Okay, so let me, quantum groups from categories. So let me just say, there'll be 6 lectures, and let me say something about the plan is for the lectures. So in the first lecture, I'll give first some motivation, from physics and gauge theory. That's okay. And then after this is some short part in the beginning, and then the main part of this first lecture will be a review of Coulomb branches. And the aim will be to prove, or at least explain, how it's possible to prove this result about counting disks in Coulomb branches. And then the second lecture will be some kind of review of kind of ideas about Fukaya categories. Then the third lecture will be about this paper, quiver Hecke algebras from a Floer homology and Coulomb branches. So this paper is on the archive. And the fourth lecture will be about this paper, Eigenlogics invariant is Kavanagh homology. And then, okay, optimistically, if we cover these things, the fifth and the sixth lectures will be about this title, quantum groups and flat categories. And these are about things which are not yet available. Okay, so that's the plan for lectures. And so let me get started with somehow some motivation or context for this business. So there's a kind of old story in this mathematics or in physics or whatever, where you study a 4D gauge theory. And you reduce along 2 dimensions. And having done so, you arrive in a description of this 4D gauge theory in terms of maps from a surface to, in other words, kind of sigma model, to a moduli space associated to 2D gauge theory. So basically, you split these 4 dimensions into 2 dimensions times 2 dimensions, and then you have maps from these 2 dimensions into the configurations of the field along the other 2 dimensions. Okay, so this is some kind of in the literature, this goes by the names kind of adiabatic limit, or sometimes TF Floer. And there's famous examples of this. So the Seiberg-Witten theory, that's some four-dimensional theory, and when you kind of, so to speak, apply this this kind of construction to it, you end up, so this construction was, this idea was applied to it by Ožvath and Zava, and you end up with what's called the Hegardt-Floer theory, or in other words, Fukaya categories of symmetric products. So here the symmetric products are the configurations of the fields in the kind of these two dimensions, and the disk, which is at issue in the Fukaya category, has to do with the other two dimensions. So that's one instance of this theory. Well, you can begin with the Donaldson theory. And this is the original thing that was called the TF Floer. And I guess, yeah, in some sense, it's a thing called a TF Floer. Let me erase that. So maybe the whole kind of thing is a TF Floer. So Kronheimer and Moravka did one such reduction and showed that you get something which is not quite Kavanagh homology. It is not quite Kavanagh homology. You might expect it to be Kavanagh homology because this Donaldson theory has to do with SL2, and Kavanagh homology is some kind of categorified knot invariance about SL2, so you might have optimistically hoped that this would be Kavanagh homology, but it's not. And the fact that it's not motivates this last thing, which is you can take the Haydas-Witten theory. So there's some other gauge theory. Haydas-Witten. So strictly speaking, this is a 5D theory, but this 5D, it's really kind of 4 plus epsilon or something. And you can do this reduction, and this reduction was considered by Gaucho and Witten. And if you do this, now you arrive from maps from a surface. So before I was splitting 4 into 2 plus 2, and now we split 4 into 2 plus 3. So you arrive at maps from a surface into some kind of moduli space of, and in the moduli space, which it is, it's called the Coulomb branch of a certain 3D gauge theory with it'll be the Coulomb branch with a potential. And the kind of, we will see in these lectures, if we get far enough, that from this you do in fact get Kavanagh homology. Okay, so that, but let me mention also so this is one road to consider this question. Let me a different road to consider this question kind of comes from some considerations of Aganagic and Akunkov. That's kind of maybe the another route. So you can consider the additive Coulomb branch. So the additive Coulomb branch you can consider the quantum connection. Of this, and it's a result kind of coming from this kind of theory of Malek, Akunkov, etc. Malek, Akunkov, etc. This quantum connection is the KZ connection, or the QKZ. Okay, and so the general story is that the quantum connection on one side is supposed to be the Gauss-Menin connection of the mirror. So this QKZ connection should be, so this is general mirror symmetry. So this another root is due to Hagenacek. By mirror symmetry, this has to be the Gauss-Menin connection of the mirror. And the mirror is kind of by general principles, which maybe I'm not so confident about why these general principles are believed, but by some general principles, this mirror will be the multiplicative Coulomb branch plus a potential. Okay. And Gauss-Menin, when you have a potential, it's like whatever, it's this thing, some exponential Gauss-Menin connection. And there's some version of Gauss-Menin connection suitable to the situation with the potential. And the point is that there's a thing which decategorifies to the Gauss-Menin connection. So what is Gauss-Menin connections? You have a family of algebraic varieties or varieties with potential, and you take the kind of families of cohomologies. Or in the case of potential, you take the families of rapid decay cohomology with respect to the potential. And there's something which decategorifies to an appropriate piece of this, which is the Fukaya category. Coulomb branch. Okay, and so the thing which this, so this, the thing which this tells you, and the reason Mina the reason this motivates the consideration of this is that it's classical due to like Drinfeld and Jimbo, etc., that the monodromies of this guy have to do with quantum groups and not invariants and so on. And so therefore, if you can categorify this connection, then you have a good chance of producing categorified not invariants, categorified quantum group and so on. Okay, so this discussion tells you, so this is one point of view on why this is the right place to look for this kind of categorified not invariants. And what I didn't say here is that Witten wrote this paper called 5 Brains and Knots, which is about why this gauge theory plausibly will give you Kavanagh homology. And so this is a different story about why this is the right place to look for this kind of knot in this kind of categorified not invariant, and you wind up in the same place, and that's the place where we're going to start. Okay, that's the.
Do you really mean to say QKZ there?
I don't know which one it's called. I'm just going to write KZ, okay, and then you can decide which KZ that it is. Maybe I'll put a scribble here, so you can, you can decide what's supposed to go. Okay. I mean, it's whichever thing is called it's whichever KZ connection is the one that gives you the not invariance. So I don't know which one that's called.
Well, based on that equation, it's called the trigonometric KZ connection.
Okay. Could be that one. All right. Yeah, so now that's kind of the whatever the motivational part of this lectures. And now I want to get started with some honest mathematics. So I don't know what people know here. So it's possible that this part is, and it's possible that both lectures today will be some kind of, each one may be completely useless for some and or all of you, but let me do some kind of review. So now this is the review about Coulomb branch. And so more or less everything about Coulomb branches is due to the works of Braverman, Finkelberg, and Nakajima. Finkelberg, Nakajima. And the setup is as follows. You fix a group, I think reductive G, and representation, like reductive group G and representation N. We're going to fix kind of this field of functions K. It's a field of functions on the formal punctured disk. And the functions on the formal disk. And we have, I'm not sure how much of this notation I'll use, but we have the punctured disk is this kind of spec, and you have to interpret spec correctly. K, and this usual disk is spec O. And there's one kind of more item of use, which is kind of this doubled disk. I'll just write this symbol for it. This is the doubled disk. Which is D union along the punctured disk with itself. Okay, so these are the ingredients of this story. And then you're supposed to consider the space. So in general, we're going to write bun G n, and this is like on X, and this is the moduli of G bundles on X plus a section of the associated N bundle, some kind of representation theoretic gadget. And this Coulomb branch, maybe it's good to observe that if I take bun G and I take a kind of tripled disk, so this is a tripled disk. Okay, and then this tripled this tripled disk contains kind of copies 1, 2, 3. And then the way this works is that you have 3 kind of maps to this bun Gn, kind of this double disk. You have 1, 2, and then you have 1 to this bun Gn, and this same thing with 2, 3, and then you have this bun Gn. 1, 3. Okay, so this, and whenever you have something like this, you get a convolution product on this one by you pull back this copy and this copy. So you have like sheaves or functions or whatever on this copy and this copy. You pull them back, you tensor them, and you push them forward. So this diagram, it gives you a convolution algebra structure on kind of, we're going to use K-theory of Bun Gn of this thing, or at least it would give you that if this was something which you could define. So, I mean, you can make sense of this, but it's not the kind of thing which has a sensible K-theory, so there's some technical issues, whatever. I won't be going into those very much, but okay, so, and from anything I've said so far, it is not obvious that this algebra is commutative, but these guys prove that. There is some kind of conceptual physical reason why it's commutative, but to see that, you need to think about some higher, I mean, anyway, it's true. So in this turns out to be commutative after to have an actual definition and be commutative. And we define the kind of multiplicative Coulomb branch to be a spec of this thing. Okay, so that's. I'll say a few more words about. Will I say a few more words about that? I'll say a few more words about how people actually define this thing. What? Yeah, I'll write. I mean, in this formula, if this made sense, nothing would be equivariant. But you know, it's some infinite dimensional space, mod some infinite dimensional group, and indeed you can deal with it by writing some equivariant K-theory. So let me write that. So what people actually do is they take, what these BFN actually do is they take this A GN. So okay, maybe how do you arrive here? The definition there. Another way to write it would be that it's the K-theory of N O mod G O times N K N O mod G O. And so if you kind of formally manipulate these symbols a little bit, you arrive at the expression. I mean, instead of taking the quotient inside, you can take it in equivariance. Get this formula. Okay, so this kind of sum. And this thing in here will denote our Gn. And because O, when you do kind of equivariant K-theory with respect to some group, doing it for some, like the affine, the equivariance for like A1 like that doesn't do anything. So this is the same as just putting G here. Okay, so the only reason I wrote this is that I wanted to explain. Okay, so one writes this formula, but to do any kind of actual calculation, you need to get your hands on some elements of this guy. So the reason I wrote this is to explain to you how you get your hands on some elements. And one way is that there's a map from the equivariant K-theory of a point to the equivariant K-theory of anything. And this thing is functions on T mod W. Okay, so one T being the torus and W being the Weil group of this reductive group. And so this gives you one big supply of elements in this algebra. And the other main supply of elements in this algebra, so writing the corresponding thing on spec means you have this kind of G and star maps to T mod W. So this is one of the main structures of this thing. And the other main supply of such elements is that, as you see this thing, one place it maps to is GK mod GO. Okay, so there's another map here from kind of the K-theory of, maybe the equivariant K-theory of GK mod GO. And one kind of thing which lives inside here, so this thing is called the affine Grassmannian, and one kind of, it has a certain stratification, and so there's these Gur G lambda, and when lambda is what's called they're indexed by co-weights, and when lambda is what's called a minuscule co-weight, this doesn't matter what you know what it means or not, because the next thing I'm going to say is basically its definition. A minuscule co-weight, this Gur G lambda is closed, and so can take the class of O, the structure sheath of Gur. This O is not the other O. Gur G lambda, that's a class in equivariant K-theory. And it gives us an element here by pulling back. So this class gives us an element which is called R lambda, and it's the monopole operator. And more generally, for equivariant vector bundle on this Gur G lambda, same thing. And then so you get elements R lambda V for such equivariant vector bundles. Okay, so these are the main two ways to produce from general considerations functions on the Coulomb branch. You pull back. Some come from the equivariant K-theory of a point, or you pull them back from this thing, and other ones come from these monopole operators. And of course, these are, just looking at the discussion we've had so far, these are, of course, these are going to be more complicated to think about. Okay, so that's the source of this, how people work with this thing. And there's one last important move that, so far I've told you the names of some elements. Yes, maybe I should mention two examples where you can just write this ring explicitly. So, example, this is in this BSN. Let's take T a torus, and N some representation, and its weights are going to be some CI. And weights are, of course, characters of the torus. I put the upper star for characters and the lower star for co-characters. And then, so in this case, the fact is that the Coulomb branch, this A star T n, is generated by the R lambda. So these are lambda. So when it's a torus, everything is minuscule. There's no need to have this discussion. For lambda, and these are co-characters. And so it's kind of generated over OT. So we have here we have a torus, there's no wild group. And we have among the functions of the Coulomb branch is this OT. Wait, let me just try again. I told you before how to get two kinds of functions. There's the OT kind of functions and the monopole operators. And so the statement here is that those generate, and with the only relations being the following. R lambda R mu is R lambda plus mu times some formula. Okay, so this formula, and you don't have to try to remember this formula. It's just to give you an idea of the level of complexity of this kind of thing for the simplest possible kind of group and its representation. These y's are the what did I write? Yeah, these x's are these characters, and y to the xi is just how I denote the function corresponding to that character. So a character of a torus gives a function on the torus, and that I write y to the xi to mean that function. The only thing I have to tell you is what is this thing. And so d xi lambda mu is either 0 if xi of lambda, xi of mu have the same sign. But these are just integers. And it's the minimum of their absolute values. Otherwise. Okay, so this, so that's one kind of simplest example of this kind of business. And the other example where you can write a formula is this kind of case of this pure gauge theory. So this is this A G0. And by whatever discussion this is here, this is the same as the G equivariant K theory of the Grassmannian, which by a kind of a famous result of Bezrikov-Nikov, Finkelberg, Vivek, is given by the following formula. You take functions, and p check times t, and you adjoin this e to the alpha check minus 1 over e to the alpha minus 1, where the alphas are roots. So one of these is a character and one of them is a co-character, so they're both functions on here. And you take the W invariance. And so when G is GLN, you can write something really explicit. It's C. It's the kind of polynomials in two variables. And then you invert the following quotients. And then you take symmetric group invariance. Okay, so these are the two times when you can just write a formula for everything, and if you take some small dimension or whatever, you can try and compute with it by hand. Okay. Are there any questions so far? Okay. Let me to anyone who hates this kind of stuff, after the end of this talk, you can forget it all. So this talk is basically an explanation why, even though I'm giving some kind of lecture series about Coulomb branches, for the rest of my lectures, you're never going to have to think about this stuff. If you like this stuff, well, at least you get one lecture of it. Okay, so then I should explain. So here were two particular cases, and now how in general do you think about these gadgets? The main remaining tool is what's called a Booleanization. So by messing around with this kind of, like there'll be maps between the G Coulomb branch and the T Coulomb branch and so on, following immediately from the definitions. And by messing around with this stuff, eventually you can show the following fact. It's not a hard fact. This is I don't know how hard it is. Anyway, it's a fact of these guys. And the fact is there's a map which is called a Booleanization from the functions on the G Coulomb branch to functions on the simplest possible Coulomb branch, which is the T Coulomb branch for the zero representation. After inverting, so this is an inclusion. After inverting some after inverting some functions. And which functions you have to invert this kind of y alpha minus 1, where alpha is a root. And I think you may also have to invert y xc minus 1. I'm not sure you have to do the second thing, where c is a weight. OG, wait. I'm not sure you have to do the second thing, but you definitely have to do the first thing. Then there's so along with this, there's an explicit formula, which I'm not going to write here. Explicit formula for the abelianization of these R lambdas. Okay, so once you know this thing, you can do all your calculations here. There's still the issue of characterizing who's in the image, of course. Okay, that's some separate story. But at least in principle, all your calculations can be done in this place. And what is this place? This place is like polynomials in 2 variables with some things inverted. Okay, so some very explicit place. All right. So while let me say this kind of the geometric version of this statement. Maybe it's a bit. It's a related statement, actually. Maybe even a bit sharper statement. What happened to this thing? So the most important structure about this Coulomb branch is the following. So okay, let me first discuss some kind of general setup, which is that this, so we have this Coulomb branch. I'll start over here. This Coulomb branch. Yeah, okay, yeah, sorry. Sometimes I put them as subscripts and sometimes I put them as in the parentheses. It means the same thing. This thing sits over this T mod W. And I'm going to take a cover. Of course, this has something to do with abelianization. This cover. And inside this T, there's 2 kinds of hyperplanes in here. This kind of root hyperplanes, and this I'll call it root of G hyperplanes, and the weight of N hyperplanes. So again, functions on the torus are its characters, and which the kind of thing that roots and weights are. And so those are functions on this torus. They can take the hyperplane when one of them vanishes. And these are 2 kinds of hyperplanes. And the basic structural fact, also as everything else due to Braverman, Finkelberg, Nakajima, about these, there's some kind of structure theorem. Which is that, let's call this map pi tilde. So, so away from these hyperplanes, pi tilde is kind of canonically isomorphic to a trivial T check vibration. That, I mean, one proves of this kind of statement here. 2 is that away from all but 1. So I remove all the root hyperplanes and all the weight all the root hyperplanes and all the weight hyperplanes but 1. So in other words, I do something that's all but 1. Let's take T minus all but 1 hyperplane. So over this thing, if the hyperplane which is left is the root alpha, this kind of m tilde g n on T minus these others is the same as the corresponding thing would have been for just the group G alpha and the 0 representation, where G alpha is the group with the same torus and only the root alpha. Okay, so it's like the I forget what that thing's called. It's called Levy. Is that what it's called?
Say again?
What's the name of this thing? It's the Levy for alpha. I forget the names of these.
It's like a root subgroup.
Yeah, root subgroup. Okay, yeah, something. This thing. So this one, and if it's a weight. C, then instead you take the same thing. Yeah, I won't write this again. In that case, this thing is isomorphic to of course, this thing also restricted to this same locus. G alpha, now it's T and C. Do the same thing, T others. Where this thing is the weight space, I mean, the kind of, this is the sub-representation of weight C. Okay? So this discussion tells you that if you want to understand this Coulomb branch in the complement of a codimension 2 locus in the base, in the base T mod W, if you're willing to pass through this cover, then it's enough to understand Coulomb branches which are pure gauge and have only one root, or in other words, just SL2. So it's enough to understand pure gauge theory for SL2, together with the Coulomb branch for a torus with a single weight space.
What if your weight space, weight is a root of your group?
Yeah, I assume that that's not the case. Okay, all but one hyperplane and no root is a weight. Thank you. Yeah. Okay, and then there's a couple more things to say about this subject. Yeah, so I have to mention like one kind of last ingredient, which is this deformed Coulomb branch. So deformed Coulomb branch. And this has to do with, so now still you have this G, and but now you have some additional group action commuting with the G action of what's usually called the flavor torus. When you have this situation, now this G and I mean, how to say, like this T, you could have put it here, but then for beta in TF, you can do the you can do kind of a TF equivariant, this equivariant version of all constructions. Whatever you get is some kind of M, which, and I don't know, hat, Gn, which now sits additionally on top of TF. And if I, because, I have a copy of the TF equivariant K theory of a point acting on everything. So that means this guy sits over TF. And if I choose some point beta in TF, then the preimage of this point is by definition this M, G, and T beta. And I write that only because you can mostly ignore this. But the thing that we'll actually use will be some kind of deformed Coulomb branch. The reason why, I'll come back to this in 1 second. So now let me discuss quiver gauge theory. So I'm going to explain to you one particular source of pairs G, N for this subject, quiver gauge theory. Okay, so actually we're not going to do any gauge theory. I'm just going to write a quiver. So we'll have some kind of quiver, maybe something like this. And so this is the original quiver. And then we do something called framing the quiver. It's this. Okay. So on this, from this data, and then we specify a dimension vector, and we specify it like this with D1, D2, D3, D4, M1, M2, M3, M4, and okay, and then this G for this setup is the product of GL PIs, and it acts on the kind of by change of basis on these. Then this N is, as usual, it's how to say, it's the space of these the sum over the arrows, maybe original arrows, I to j, c di, c dj, and then plus I, c m I, c di. Okay, so this thing. So, and then this guy acts on this guy by change of basis. And T, this TF is kind of the tori which act up here. Direct sum, C star to the MI. And then the space that we use is we take this, for this stuff, we take the Coulomb branch for G, this N, some beta, and we delete the locus where this monopole operator is 0. Okay, so we take some particular locus, and the reason why you don't have to care very much about this deformed Coulomb branch business is that it turns out, let's call this part just M. Turns out that this thing is just the same as this. But there are some structures. Which are more visible from this description. So that's the only reason why this description is relevant. Okay, so I won't dwell too much on this kind of deformed Coulomb branch, except to say one last thing about it, which is that so before I said about this kind of structure theorem, and in this deformed case, there's a similar story, except there's one more kind of hyperplane, which has to do with when your fixed weight up here coincides with some action here. So there's one last kind of hyperplane you have to discuss. And that one last kind of hyperplane, it corresponds to this structure. So, the away from codimension 2 in the base, the entire story looks like one of these three structures. Okay, so that's the outcome of this kind of structure theory. So I've gone a bit. When did I start this lecture? Should I stop here and then continue in the next lecture? Yeah, okay. So I didn't get quite as, what I'll do, I still have to explain about this. So this is basically a review of existing knowledge of Coulomb branches. In the next lecture, I will begin by spending a few minutes explaining about this, how to count disks in Coulomb branches. It shouldn't, I mean, after all this discussion, it won't take very long, and then I'll start reviewing about Fukaya category. Okay, so the last thing I want to say about this Coulomb branches is I want to describe how to study holomorphic curves in there. So let's see. So in the case at hand, maybe first I'll, so in the case at hand, this Coulomb branch, whatever it is M star G n. We're in some situation where G is a product of GL D. And so it sits over some C star to the D1 mod W mod S D1 cross C star to the D2 mod S D2, so on. And I want to study maps of a holomorphic curve, holomorphic maps of a curve into here, F. And so first, let me remind you how to think about maps like this. Okay, so this is what's in the literature called the cylindrical model. In the context of Hegardt-Floer theory, it was introduced by Robert Lipschitz. But somehow, in the more general context of algebraic geometry, it's ancient. And so it's about how to study, just in general, if I have a curve C, so C is a curve. It's not so important it's a curve, but okay, so we want to study the sim n x, and okay, x for us will be also a curve. Then the claim is that such a thing is equivalent to, I take, so what is such a thing? It's on each point of C, I have n points of x. Right? That's what is such a map. So I have C, and above each point of C, I have n points in x. Or in other words, I have C, x, and I have some kind of n to 1. I have some locus inside C times x, which projects n to 1 to C. Okay, that's what the data of what is a map from C to the symmetric power. And so let me just say that such things are the same as a curve S maps to C with degree n, and it maps to x. Okay. And if I have many different of these factors, then I want one S for each of the factors. So that's how I'm going to encode maps like this pi. This pi composed, what is that right here? This is pi composed F. And so the question I'd like to discuss about here is, given a map from C to some product, a symmetric product, so product sim D C star. When does it lift to a map C is M cross Gn? And I'm going to answer this question under some simplifying hypothesis, which I would like to be able to remove, but will be enough. I don't need to remove it to do what I will do now, I mean, for the rest of this lecture series. So assume, let's call this G. Assume G is transverse to all hyperplanes mentioned earlier. So all this kind of root hyperplanes and weight hyperplanes and this kind of deformed hyperplanes and so on. So we're going to make this assumption. And the most important part of this assumption is that the image of G is not completely contained in one of those hyperplanes. So I could probably do almost everything without actual transversality as long as the curve is not fallen into a hyperplane. Okay, then so let's write CO for the inverse image of, maybe I'll give this a name so I can stop writing it. I'll call this B. That is B minus the hyperplanes. I guess they're not planes in B. They're hyperplanes on the cover. I mean, they're hyperplanes in here, but then when I go down to this quotient, they become like this kind of thing with discriminant singularities. The usual story. Okay, so let me look at this C on this locus. And I told you that away from the hyperplanes, it's at this kind of trivial T-check vibration after passing up to this cover. So on this locus, so a lift of C O, call this G O to B O to this C O to this M G N. What do I have to do? Well, the data of this downstairs map was a map. So the data of this downstairs map was this kind of thing. And this fiber, after I go up to the cover, is just trivial. So I'll just say again what I said last time, which is that the data of such a lift is equivalent to a map that maps from each Si. So as I said, there's one of these S's for each of those factors of the symmetric product to C star. Okay, because the kind of fiber has the same kind of the fiber is trivial, and there's W action on it. Okay. So the only question, question is which such SI, which such maps extend to maps to this M star G. And I'm just gonna, I'll just state the answer, and then say some words about how to prove it. So the answer, the map extends if and only if so maps, let's call them phi u I s I 0. I write this U to distinguish from this base C star direction, which I would call C star Y. So the map extends under the following condition, that there should be, so phi is, after all, each phi is a map from a curve, and it has simple poles over the kind of yeah, I'll just write. I'll write some notation and I'll tell you what it means. Two simple zeros over I and 3 phi u I. Yeah, no, I'm calling it phi u. I'm just going to call it phi I. Phi I, phi j, which is a map from S I times Sj, identifying over C. So this is a curve again, to wherever. This product on this fiber product has simple zeros. At S I to J. Okay, now just to explain what these notations mean, the phi I, it's a function valued in C star. So it makes sense to say it has a polar is 0. This Si is the locus where one of these points falls in the root hyperplane, according associated to this a root hyperplane associated to the node I. And similarly, this one is for the hyperplane corresponding to this deformed, this kind of new deformed hyperplane, associated deformation. And this is a hyperplane having to do with the representation. Okay, so for like so does it make sense what I just said? So this curve C, it maps to the base. Inside this base is a bunch of hyperplanes. I said C goes there transversely. Going there transversely means that whenever C has hit one of these hyperplanes, only one point of these n to 1 cover kind of goes in there. And so I take the corresponding point on S. That's what it means, this SI, SII, and so on. So it's some particular points on this guy. And yeah, that's the condition. And let me just say some, I don't want to say too much about how you prove this, but the way you prove it is this this hypothesis that it meets transversely means, in particular, I mean, I have a curve meeting some divisor, so it meets it in the complement of codimension 2 in that divisor. So it meets only generically along that divisor. So I'm always in one of these pictures, okay, like according to this kind of structure theory. And because I'm always in one of these pictures, checking this reduces, so this, the proof that this is true, so proof, the kind of structure theory, this BFN reduces you immediately to checking the analogous statement for the following quivers. You have this, and this. And these are all, and you just check by hand. And you write in coordinates and check by hand. In particular, those examples are all either abelian or pure gauge theory. So you can write the Coulomb branch explicitly. Okay, so and that's what you do. Okay, so that's this characterization. Let me say that it would be useful to extend this answer beyond. So okay, let me preface that by saying this correspondence in the this kind of cylindrical model in the for the symmetric products, that's easy. You don't need to make any kind of hypotheses about transversality or whatever. You can do that everywhere. But this one I don't know how to extend at the moment, and it would be very useful to do that because so when you're doing kind of usual Floer theory, like we're going to do here, you can perturb all the Lagrangians in order that everything is transverse and so on. That's fine. And so this will be enough for you. But if you want to do Floer homotopy theory, then you need moduli spaces of disks of all dimensions. And then you cannot ensure that, you know, like such a moduli space will contain maps which are not transverse to these divisors. And so it would be good if I could reason about that as well. And a reason that one might want to think about that is to think about whether or not this theory, if you just, I mean, everything I say could be, from now on, could be said in Floer homotopy theory. And you can ask if you get the Kavanagh homotopy type. I don't know, and in order to know, I would want to know the answer to this question about how to extend this. Okay? So all right, so that's the end of this discussion of the cylindrical model for now. I'm going to do some kind of bit of review of some basic notions of Fukaya categories and how to calculate some things, and do one kind of interesting calculation in this world in the rest of this talk. Okay. what to say about category. So whatever it is, it's a procedure which takes as input a symplectic manifold, and it gives you as output an A infinity category. And if you've literally never seen this before, the kind of the ingredients are, you have Lagrangians. These go to objects, intersection points, L intersect M, goes to Hom M, and kind of holomorphic disks. So the disks, their boundaries should travel along the Lagrangians, and their corners should go to the intersection points. Infinity structure. And the cartoon of this is if you have three Lagrangians, L, M, N. So this is an element of Hom L, M. This is an element of Hom M, N. This is an element of Hom. So you can read it. You can read it both ways, right? But I'm going to use this as an element of Hom Ln. And this disk. So when you try to write the composition, Hom Lm tensor Hom and Hom Ln, then if you take kind of P, Q, R, P tensor Q will go to sum over T, where there exists kind of the class of a disk with corners, P, Q, T. And in this case, it'll be R times T. Okay, so that's how it works. Yeah, there's all kinds of complexities and so on with this business, but I won't dwell on them. Let me instead do the one or two basic calculations which are going to be relevant. The calculations you should know from maybe I should say something else about I should discuss what's called wrapping. So the way this works is the following. If you have, so before I had X, which was a symplectic manifold, but now I ask it to be exact symplectic. And in this situation, there's a vector field called the Liouville vector field, which has this property. There's the Liouville field. And we typically restrict attention to the situation where kind of you have this picture, this is X, and the Liouville vector field looks like this. Okay, it kind of goes out. So the typical example, so example X is a cotangent bundle. Now, what about wrapping? So let me just draw a picture. So here's a picture of the cotangent bundle of S1, where I kind of identify these places, and this is the zero section. And the typical kind of Lagrangian, which you're interested in this exact symplectic setting, is a Lagrangian, or Lagrangians which are eventually conical. In other words, at the outside, they can do whatever they want in the inside, and then at the outside, they're kind of parallel to Z. So in this picture, Z, this vector field Z looks like this. Wrapping. So maybe I'll explain it this way. When you the first problem. Well, I said I wouldn't dwell on the problems of the Fukaya category, but the first problem is that this picture is pretty good if your Lagrangians intersect each other transversely. Okay, then indeed they'll meet at some kind of finite number of points, and it makes sense to have this discussion. But in a category, among other things, you should have a self-Hom. And the Lagrangian does not meet itself transversely. So that's the first problem you encounter. And you can resolve this problem in various ways. One way is you perturb your Lagrangian and then try and argue that the result was independent of perturbations. And this is fine when you're in the compact, when X is a compact, when you have a compact symplectic manifold. And you just perturb by any Hamiltonian, you use that, and then you argue it didn't depend on the perturbations. But in the non-compact world, you know, if I perturb, then something happens at infinity. And it turns out I don't want to dwell on it, but it turns out that you want to perturb positively at infinity. Okay, because like, roughly speaking, when you perturb positively, so when L plus is a positive at infinity. A positive at infinity means you go this way. Perturbation of L. Then there's a kind of canonical map from L plus to L. And the source of this map is basically kind of this positive perturbation. Let me not dwell on it. So there's such a map. And it's like if you view this perturbation as being the graph of a Morse function in the neighborhood of L, then such maps correspond to intersection points, and one of them gives the unit. And when you're thinking about Morse functions on non-compact manifolds, you want to impose some condition at infinity in order that you compute cohomology with your Morse function as opposed to homology, and so that there's a unit. And anyway, so that's about this. But then you could discuss how much do you positively perturb. And you know, if you positively perturb a little bit, well, let's not have this wiggle anymore. If you positively perturb a little bit, and that's great, you have one intersection, which is good news because you know you want to define self-Hom, and self-Hom should contain at least the identity, and so that's great. But if you want to start composing things, then if I want to compose this Hom with someone, I better perturb again. And if I want to keep composing, I better keep perturbing. And for a while, the intersection of any two of these is 1 point. That sounds good. But after I perturb enough, eventually, I'm going to start seeing this. Okay. And so now it looks like what the harm is may depend on how you perturb and how much you perturb. And there's basically only two consistent ways to make a choice of how much you perturb. You can either perturb infinitely, or you can perturb infinitesimally. Those are the two choices. And we're going to perturb here kind of infinitely. So it's kind of wrapped. It's like it's one consistent choice of perturbation to make things defined. So you define Hom Lm as some kind of limit of Hom L plus M over this kind of L plus to L positive perturbation. Okay. So that's the wrapped category. And let me also discuss a bit about partially wrapped. So again, I'll just have this discussion in kind of a picture. You can fix additional data at infinity, and so for example, maybe I'll fix this kind of stuff. And if you do that, and then I discuss wrapping, partially wrapped means I kind of go as much as possible until I hit one of these blue guys. Okay, so that I kind of wind up with this picture. And yeah, okay, so there's a good theory of doing this, and if you want to learn about it, you can read my papers with John and Shield. So this makes sense. I think last time I was here, I gave a couple lectures about this subject. But let me tell you the two facts. Basically, for the rest of the discussions here, there's about two facts you need to know about wrapped Fukaya categories and partially wrapped Fukaya categories, which is how to compute them in these examples. So, facts. This kind of a Fukaya category of P star S1 is modules over C inverse. Type 1, type 2, as with the Fukaya category of P star S1, one stop. And just to make clear what that means this picture is modules CT. And let me just, this is one of these are some of the oldest facts known in the subject. And let me just remind you how you, if you want to learn these facts carefully, I think there's some survey of Aru called like Beginner's Guide to Fukaya Categories or something. But let me just draw you some pictures about this stuff. So, okay, so you have you have a Lagrangian, you have the wrap version, which kind of goes around. Okay, and then there's kind of z many intersection points, so z intersections. So that makes it makes it plausible that endomorphisms of the cotangent fiber is ZTT inverse, the kind of 1 for each power of t is plausible. And then to check this, you have to take some sharper wrapping, where it kind of goes even faster, and count. So the old way to check it, which is just to check, you count holomorphic disks. Okay, so the one thing you should know about counting holomorphic disks is that holomorphic disks in general are impossible to count, but in the plane they're very easy to count because this Riemann mapping theorem tells you that anything that looks like a disk is a disk. That's the basic principle by which you count. But let me just tell you, a way to convince yourself that this is true. And for that matter, the other thing is true. So this has nothing to do with this lecture series, but let me just convince you that this is true without counting this disk. Okay? So it's better not to count disks when possible. So let me convince you this is true. So the way to convince yourself this is true is the following. I'm going to put 2 stops. And I'm going to consider 2 Lagrangians. Kind of a straight one. And one that goes once around. Okay, and then it's easy to convince yourself because I've kind of put these stops here because I've put these stops, there's not this kind of infinite process of wrapping. Okay, so it's easy to convince yourself that Hom, this kind of white one with itself, is one-dimensional. Hom, the red one with itself, is one-dimensional. And you can see visually that Hom, from the white one to the red one, is 2-dimensional. Remember that when you compute Hom, so this Hom is not symmetric. You might have thought that Hom from the red one to the white one should also be 2-dimensional. When you compute Hom, what you do is you wrap the one in the first factor as much as possible. So here I've wrapped the white one as much as possible. But if I would instead have wrapped the red one as much as possible, then I would see this picture. And so there would be no Homs. Okay, so Hom from the red one, the white one is 0. So this is some kind of lesson in this subject, which is that it's a lesson irrelevant to these lectures, but it's a lesson in this subject that to compute, it's a good way to compute is put in more stops to kind of stop as much wrapping as you possibly can, compute there. It should be easy, and then you do something else, and something else which you do is, okay, so first let's discuss this category. So this thing is kind of modules for, this calculation tells you that it's modules for this quiver. Okay? And if you think a little bit more, the kind of object of this category which represents this vertex is this guy, and the one which represents this vertex is this guy. If I wanted to go from this kind of partially wrapped case to the wrapped case, I claim you do it by taking the quotient by this object. And the reason is something that is relevant for these discussions, which is that when you take the cone between two Lagrangians like this, taking the cone on that morphism looks like doing that. That's some like basic fact of this subject, which, okay, maybe I'll justify later. And what did that do? That let me rat past the stop. Okay, so going from this stopped world to the not stopped world can be done at the cost of a cone with this yellow guy. And if I take the quotient where the yellow guy is 0, that cone is free. So that was the argument that this category modulo, so this statement's true as written, and this follows from this kind of geometric discussion that this thing is this wrapped category, okay, this wrapped guy. And well, what is this? This is coherent sheaves on P1 by a kind of old calculation of Bailenson. And what are these? Well, I told you those are the representing objects of these. So this quotient is coherent sheaves on C star. So that's if you don't want to do this calculation, which is not a hard calculation. Okay, so you should, as an exercise for yourself, do this calculation. But a different way to convince yourself that the thing I said is true is you compute somewhere easier and then you remove the stops. Okay, so now I want to talk about, that's more or less, we're going to see many more examples going forward, but I wanted to at least say some words about this. Now I want to do I want to illustrate the new phenomena that appear in the kind of calculations we're going to be doing tomorrow. So, okay, so I'm going to make a calculation in the kind of simplest possible setup, which is basically this. So yeah, okay, I have time enough for this discussion. So I explained that this kind of this kind of Coulomb branch. So we're going back now to this Coulomb branch. This thing had some kind of locus. It's M star G and O, which is like T check times some TO mod W. Right, that's what we discussed. And so to describe Lagrangians in here, I'm going to do it by giving Lagrangians in here. And to give a Lagrangian in here, I should give like a W equivariant Lagrangian in here. Okay, so that's how I'll describe them. And in our case, this T check cross TO, each of these things is just C star to some power, and the same power. And so the way I will describe Lagrangians is is by drawing a picture inside C star. So, okay, so let's do it. Here's I have to have two copies of C star, and I'll always draw them like this. There's the C star kind of base copy, so C star base, like this. And then I have a C star fiber, which for some reason I'll draw like this. And then to indicate what was this O? This O was I delete a bunch of hyperplanes, and how I record that information is so what were the hyperplanes I deleted? Maybe for most of the rest of the lectures, for rest of lectures, I'm going to restrict to the case of the most. I'm going to restrict to the case where this quiver is just one node. And so I only have now two of those kind of hyperplanes before. I have the root hyperplanes, which is actually the most serious. God, no, this is true for now. But the root hyperplanes, and I have these kind of deformation hyperplanes, the ones that came from this this thing. And so the root hyperplanes, to avoid those have to do with the place in the symmetric product where 2 points collide. And so to avoid those, I should just ensure that whenever I draw pictures, I'm not kind of colliding my items. So in other words, if I draw any picture like this, there's a Lagrangian. This picture gives me a Lagrangian in sim2 C star base, just the product of these two things. And it's a Lagrangian, moreover, which stays away from this root hyperplane. So like no point on this is the same as any point on this. So this defines this picture gives a Lagrangian in sim to C star base minus this kind of root hyperplane. Okay, and this kind of deformation hyperplanes, those correspond to the names of certain points, and I just draw those points, and my Lagrangians should avoid them. So long story short, this picture describes for you a Lagrangian in here, and therefore in here. But that's how I'll do this work. But that's some kind of general story. But now I want to tell you there's one example calculation, which is going to be even easier than this. In fact, there'll be no symmetric powers, just this kind of deformation divisor. So I'm going to consider the following thing. So I'm going to consider this situation. This is something which is associated with this quiver. And so what kind of pictures I should draw should be 1x in the base, some fiber, and I get to draw a Lagrangian here times a Lagrangian there. That's how I define an object. And so I'm just going to draw an example. So this Lagrangian times this Lagrangian. This is an example. An object. I'm going to call this object U. And then I'm going to draw another example. This same picture, this x. And this. Now I'm going to draw this. and something in the fiber. Maybe it's easier if I draw in some color. I'll stay from there. Okay, so the Lagrangian in the fiber. So I'll call this J. And this one has some kind of unambiguous meaning because I stay away from all this bad loci. This one is more worrisome because I go to the bad locus. Let me not. What happens? I mean, like there's two things that are worrisome. One is that one is that this thing in the base just stops at some random point. That's not allowed usually for the Lagrangians. And the other thing is that I've gone to the bad locus. But in fact, these two problems cancel each other out in that the way this works is that this, as you go to this kind of bad locus, this guy goes off to infinity. So it turns out to be okay. But so let me. I want to show you a disk count which is involved in proving. So here's a kind of a fact which is irrelevant to the rest of this lecture, so you don't have to worry about whether this object makes sense or not. But it's the easiest illustration of the new phenomena in the disk counts. So the fact is that U is isomorphic in fact of J. And I want to show you one of the, like how do you prove that two objects are isomorphic? You have to show there's a Hom in one direction and a Hom in the other direction, which together compose to the identity, and also in the other way. And that means I have to compose two Homs, and that means I have to count some disk. And so I want to show you that disk count.
So in the J, I thought this is the product of the Lagrangian and the base and fiber.
Yes, this times this.
Yeah, why is this going to that point?
Yeah, so how to say? So the fiber over this point, I suppressed this part of the discussion. I'll have to maybe bring it back tomorrow, which is that there's also some superpotential in this space. And this superpotential it means you have to do some wrapping. And there's wrapping, you do some wrapping and it's stopped by something. And the stop looks like this. Okay? And if that stop, no. I guess it doesn't matter. Yeah, here. If that stop were not there at all, then what am I doing? I'm trying to this yeah. So this is the Lagrangian which links that stop. So if that stop were not there at all, this guy would be zero in the Fukaya category. If we were just discussing this cylinder and just studying his Fukaya category, and that stop were not there, this would be a zero object. But with this stop, it's not a zero object. But what happens at this point is, at this point, the superpotential, it kind of, it gets a critical point at infinity. And so kind of in this fiber, it's as if that stop is gone. So if you think about the geometry, it's kind of a long story, but if you think about the geometry, you can set up this Lagrangian so that it goes to infinity here in a way that's consistent with the potential.
So when you go to that point,
When you go to this point in the fiber, this one goes off.
that would be a critical point.
Yeah, critical point. It's not so important. I mean, okay, it would be important if I was ever again going to use this Lagrangian J, but I've just put it so I can draw an example of a discount. So and don't worry about it too much. As I want to draw this example. Okay, so There's the base. And the base, we have this one, this one, and this one. And in the fiber, we have this one, this one, and this one. Okay, and I'm going to study this composition. There's some S, Q, P. They correspond to points here, P, Q, S. And so, I mean, the Lagrangians are kind of like this one, P and S, times this one, P and S, and that's one Lagrangian, and this is another Lagrangian. This orange times this one here, and the white times the white. So those are three Lagrangians, and P is an intersection point between the yellow Lagrangian and the white Lagrangian. Okay, that's how you read this picture. And what I claim is that the discounting rule I wrote before tells you that it's legitimate to study the kind of thing that we have as a disk is like the following. This times this. Okay? So, and also in the back. So you may, upon first sight, be concerned about something, namely, this disk is going to infinity. What does that mean? But I remind you that the way we count disks is we count like punctured objects which map to this C star with some pole condition and so on. And precisely what that pole condition is that the pole of this disk, so these two disks have to be the same disk, and the place where this goes to infinity has to sit over this point. That's what that rule I wrote down before said.
It's not a product of two disks, right?
It's one disk.
Two projections.
Yeah. It's one disk with two projections, and that disk is that disk is not C, it's S. It's like this. In this case, a one-to-one cover of a curve, but with these two projections. And now I want to explain. So there's another thing which might concern you, which is that I have convex. If you do this business, you're used to counting disks with convex corners, and I've drawn disks with concave corners. And so that you may find that worrisome because the disk with concave corners that if you've studied this stuff, that has a one-dimensional moduli space. And we're looking for rigid disks, in other words, those with a zero-dimensional moduli space. And so the reason why this picture, the reason why this picture is the name of a rigid disk, or some count of rigid disks, is the following. So, the way to think about this is we have we consider the moduli space. This is the moduli of a disk with 3 boundary and 1 interior marked point. Okay, that's this picture. It's a moduli. This is not a disk. This is a moduli space of disks. Wait a second. It will, but wait a second. So, and then on this moduli space of disks with 3 boundary and 1 interior marked point. So the interior marked point can go to the boundary in 6 ways. It can go to any of the boundary marked points, that's 3 ways. And it can also go to the intervals between the boundary marked points. So and three boundary marked points, which I'll call S, P, and Q. P, Q, S. Okay, so I'm going to name these boundaries by which, where the boundaries correspond to where the interior marked point went to the boundary, so I'll name them S, P, S, P, Q, P, Q, S, Q. Okay, so now I'm going to look at this. Consider the moduli space of maps with this image. That moduli space is one-dimensional because your disk, so if you're used to this stuff, your disk, it can when you have this concave corner, your disk can travel up like this and then turn around and then come like that. Or it can do the other thing, that when it's like going this way, it can go the other way, right? This way. So it has kind of that's a one-dimensional space, and then you can ask, where does that one-dimensional space hit the boundary? It hits the boundary when you're traveling this way, and this traveling goes all the way to this x. Because this x is the location of I consider maps of the disk, which send, as Conan said, the interior marked point to this point. So the place where this goes to the boundary is when this happens. And what is that point? That's a point between P and Q, right? So one possibility. One possibility is this is one boundary point of this base configuration, and the other boundary point of this base configuration happens when. That's when you travel this way too much, and if you think about it, when you travel the other way too much, it corresponds to that boundary point falling into S. So this moduli space, you don't actually know what it looks like, but at least at the boundary it looks like this. Okay, the moduli space of such configurations. And it could do whatever. It could be like some wiggly thing. It could have other components, whatever. And now I'm going to go through the same reasoning for this guy. So this one is about maps where the interior marked point goes to infinity. And then how does it break? Well, again, we can kind of break this way, where you see something. If you break on this side, that's a point between Q and S. And if you break on the other side, that's a point between P and S. So that moduli space looks like this. I mean, like, you don't know what it looks like, but at the end, it looks like this. And then it does whatever. It like wiggles around somewhere, and then maybe it also has some things, whatever. But the point is that we want something with both these projections. In other words, we want something in the intersection of the yellow and the white. And you can compute that intersection number knowing only this boundaries. And you compute it to be 1. Okay, so this picture shows that there's a unique such disk. The count of such disks is 1. So this picture shows a count. And so tomorrow we're going to be drawing maybe, okay, I don't know how many, but every calculation in this subject is done this way. Count of such disks is 1. And so that's how you compute some composition. And then if you can compute a different composition the other way, and then eventually you can convince yourself that these two objects are isomorphic. It's not important these two objects are isomorphic. I just explain it to show you how we count disks in this business. Okay, so I'll stop there for today.
Usually in Calculator case, this count is 0 and this function.
But that's only when you have holomorphic Lagrangians.
Oh, this is not.
Yeah. Yeah.
Can you write the domain of the curve when it breaks at two endpoints?
So let's see. We have this kind of center guy. And if I have it going, let's say, to S, what that's supposed to look like is I get a bubble with still S, the mark point, and Q, P. And so this picture is what happens here. And what happens here is is what we have S, P, Q, and then this guy's broken off here and like this. Is it okay? And you see that you see that such configurations are still one. It's still a one-dimensional space, right? Because this two boundary mark points and one interior is one-dimensional, and that's why it's like a whole interval. And similarly here, we have 4 boundary points, so it's one-dimensional. So this corner is some still more degenerate thing where there's some further breaking.